Off is the mic you're using is like usually the one you use for say lecture hall you know
It depends on the
presentations.
platform. I'm using a very high quality plug and play mic, a CM Tech mic, and it seems to work very well on this platform, and also it works on Firefox, which is where I'm running Zoom, but it seems to be less reliable on Chrome. And with certain platforms, it doesn't work at all, even though it appears to be working at my end. People can't hear me. And then I have to revert to the secondary mic that is bundled with my camera. The camera's good. That mic is not as good, but sometimes I need to use it. I mean, it's every platform has different specifications, and there aren't really cross-platform compatibilities with these plug and play devices. You understand that?
Yeah, I see. No, it's probably like web platforms, some preferences them
Exactly. And there are so many
between the two.
platforms out there, believe me. I mean, there's not only Zoom and Blackboard that we're using, but I mean, I'm involved with international conferences, and there are so many other platforms these days. They're all different. Okay, so the moral of the story is that we have to continually tweak our technologies in order to make sure we're seen and heard when we're doing, different kinds of video conferencing. But anyway, that all comes with the territory. So, welcome to everybody. I see more people are joining now. Well, I hope you all had a safe and a happy Thanksgiving. And we're going to resume this week. Now, what I have noticed from the number of views of last week's video is that Monday's plenary on the prisoner's dilemma was not viewed by nearly as many people as normally view the Monday lectures. Monday was not a holiday last week. And I also recorded a lecture on Thursday, even though that was a holiday. And that was for the benefit of those who want to follow up with the prisoner's dilemma and understand the very important development that takes place when we move from two players to n, where n can be indeed a large number. So that was accomplished last week. And if you have not yet seen either of those videos, and if you want to stay abreast of this course for the remaining week that we have, then please do watch them. Because if you are going to be interested in this week's issue, which will be basically a spin-off of the prisoner's dilemma, Newcomb's problem is a very special case, as we'll see, and a very interesting case of the prisoner's dilemma. But absent the foundational material that we covered last week, probably your understanding of Newcomb's problem will be impoverished. So I urge you, if you're interested in this problem, as well as the prisoner's dilemma, to go back and make sure you view the two lectures last week, which dealt exclusively with the prisoner's dilemma. Are we clear? Are we clear about that? All right, I'm assuming we're clear. And just some housekeeping notes on this theme. Firstly, we are going to have this week, as mentioned, devoted to Newcomb's problem, which is a special case of the prisoner's dilemma, and I'll be talking about that shortly. The last day of classes, I think, is next week, probably on next Tuesday or Wednesday or Thursday. In any case, no, not Tuesday, not Thursday, but I think Wednesday. But our last class will be Monday of next week. And that's going to be another plenary, same time, same station. And I'm not going to introduce new material next Monday, but what I am going to do is throw the session open to any questions that you might wish to pose concerning any of the material that we've covered in this third section, or will have covered. So that would include Zeno's paradoxes, Anselm's ontological argument, and the interesting objections that have been made to it, the prisoner's dilemma, and finally Newcomb's problem, which we're going to cover today and Thursday. So that's our agenda going forward. And again, next Monday, I welcome you to an open session where you should feel free to pose any questions that arise from the specific material I just mentioned. And if indeed time permits, I would be happy to entertain larger questions from you about the whole course, although they may not pertain to your third essay for my group. But it is, after all, philosophy course, and nothing is off limits in philosophy. So I will focus firstly next Monday on questions specific to the third section of material. And should those continue for the whole time, we'll deal with them. But if people have other questions that are philosophical that they wish to ask, I'll be very happy to try to entertain them and perhaps to facilitate some discussion among you. So next Monday, please bring your questions. I'm not going to lecture to you, but I am going to be available as a resource person and a facilitator of discussion. So that might be fun and I hope profitable for you as well. So that's our plan going forward. And to my group only, that is section M, that breakout group with 80 students. Our last class will also be that Monday of next week, and your essays will be due the following Monday. And again, the rest of you have your own arrangements with your particular instructors in your breakout groups about your assignments and so forth. So are we clear about the housekeeping? If you have any questions, please feel free to ask. Is clear. Okay, I see a bunch of yeses. So that's always nice. Yes is a nice word. And it means that you're clear. But if you do have questions, feel free to ask. So if everyone is all right about the housekeeping and our agenda, then let's get to it. And before I launch into Newcomb's problem, I do want to recapitulate just one thing about the prisoner's dilemma that I didn't really have time to mention last week, and that was in the context of the N person's dilemma. And it's a bit of the road less traveled in the sense that it's not a mainstream thing. Obviously the tragedy of the commons, for those of you who've seen it, and the problem of free riding, for those of you who were there or have watched the video. These are very widespread, pervasive problems that pertain to all of humanity in society. Every society is going to have sooner or later to confront a tragedy of the commons through the overexploitation of non-renewable resources or exploiting renewable resources quicker than we can renew them. We have unfortunately, lots of tragedies of the commons on every scale. And we also have lots of free riding on every scale. And last week, I was very pleased that some of you immediately saw the connection between an N-person prisoner's dilemma, in which a lot of people are defecting, and a Hobbes' state of nature. And indeed, rational choice theorists of the 20th century were very quick to make that connection as well when the prisoner's dilemma first came into the literature in the late 40s or early 50s. People began to realize that Thomas Hobbes, although he had no inkling of game theory or rational choice theory, he nonetheless did model it in his own way with his state of nature. So an N-person prisoner's dilemma in which almost everybody is defecting would be equivalent in some sense to the Hobbesian state of nature, whereas an N-person prisoner's dilemma in which most people are cooperating would also then be roughly equivalent to a Hobbesian commonwealth where people are embodied by the social contract. So that's a rather interesting connection across those centuries. And Hobbes, in a sense, gets credit, therefore, for doing even more than he had anticipated. But I wanted to say to you, and this is one more thing we didn't have time to mention. I think it's very interesting, at least for me it is, that the prisoner's dilemma in the iterated case, and you may remember that if we're talking about just playing the game once, then we call that a one-shot dilemma, because literally you're making your choice and your co-prisoners making their choice, and then you get the result. But if you iterate it, that is, if you play many rounds, and whether you're informed of what's gone on in the past or ill-informed or semi-informed, it's possible to iterate the dilemma. And if you do this in a computer modeled setting, you can actually have tournaments where the strategies compete against each other. And two tournaments famously, and this started a whole generation of interest among programmers, gamers, AI people to develop strategies, superior strategies for competing against other strategies in iterated computer simulations of the prisoner's dilemma. Two of the two earliest and most famous, therefore, were conducted, I'll type his name in, by Robert Axelrod, who may still be alive. He's a political scientist at the University of Michigan. Excuse me. And Axelrod concocted and published them in the, I think both of his, I'm not sure, I think he published them in the Journal of Conflict Resolution. I believe that's where you'll find his publications. I've misspelled resolution, but you know how to spell it. So this is in the 1980s, where he conducted these tournaments. And the strategy that ended up winning both of them, and you may have heard of this because it's worked its way into popular nomenclature. And I'm going to type in the strategy, and you're going to tell me if any of you have come across this expression, tit for tat. Is anybody familiar with it? Yes, you are. Okay, interesting. Quite a few of you. And where did you come across? How did you hear about tit for tat? Any of you who've said yes? In what context did this come up for you? From your friend's mother. Okay, well, she must have got it from a context. Now, it has been popularized, but it's not a revenge scheme at all. You heard it on a show, all right? So, I mean, people talk about it. It's not a motivation system. It's not psychology. It's a strategy. You see, it's a game theoretic strategy for which has demonstrated its robustness. That's very effective in iterated prisoner's dilemmas. Only in this computer setting. In the real world, it also may indeed have some applications. But the strategy is deceptively simple to state, and I will tell you exactly what it is so you can understand it in a minute or less. The strategy entails cooperation on the first move. And then that's right, Ramon, equivalent retaliation, or cooperation. It's not retaliation unless the other guy retaliates. You see, tit for tat begins by cooperating. Imagine you're playing an iterated game of 1,000 moves. So you begin by cooperating, and you see what your fellow prisoner does. If your fellow prisoner cooperates, you cooperate on the next move. If your fellow prisoner defects, you defect on the next move. So it begins by cooperating. And it continues by mirroring back whatever your fellow prisoner did last. So every move that you make with tit for tat is a mirror image of the previous move that your fellow prisoner made. And this will very quickly result in a good performance for this strategy. Just a couple of points to understand. The inventor of the strategy was a psychologist, and I met him. He helped me with my PhD, actually. His name was Anatol Rappaport. He's deceased now, but he was Axelrod's colleague, I believe, at the University of Michigan for a number of years. He knew him anyway, and Anatol Rappaport published several books. He did a lot of social psychology experiments with the prisoner's dilemma. He became a sort of expert in the prisoner's dilemma. So it's not surprising that this strategy of tit for tat, which he devised, won both tournaments. But Axelrod was very quick to point out, and I must also point out to you, so please don't get this wrong. The media has got it wrong because they get everything wrong. But they've all said, oh, the best strategy is tit for tat. There is no best strategy. Unlike chess, where there's always a best move, such that if you find your best move, you will either win or at the very worst draw the game. You will never lose a chess match if you find your best move at each juncture. In a competition, an iterated prisoner's dilemma competition, there is no best strategy independent of environment. And the environment precisely consists of the population of strategies that are competing. So the quote unquote best strategy will depend actually on which other strategies are in the population. So best will be a relative term in that context, not an absolute one. And you can always devise a strategy such that no matter what population of strategies you're competing against, you can always devise some new strategy that will be superior in that context. But then, given that that's the new context, you could always devise some new strategy such that that newer strategy would be better than the other one. So, whatever population of strategies you assemble to play this game, it's always the case that you could devise or concoct a strategy that would be relatively the best, but only with respect to that population. Are we clear? I hope so. I'm not going to cover this in depth, but those of you who are interested in programming and gaming and AI, you may want to look at the seminal work by not only by Rappaport in The Prisoner's Dilemma, but in the computer tournaments that Axelrod conducted. And then I developed, I went on and developed a strategy that was actually superior to Rappaport's. I have a strategy that beat tit for tat. But again, not in every occasion, just I took the very best strategies from both tournaments that Axelrod conducted. And then I developed a family of strategies whose most outstanding member was actually able to defeat tit for tat in that environment. It's a maximizing expected utility strategy, by the way. Those of you who remember maximizing expected utilities from last week, that's a very effective strategy, particularly if you begin with a cooperative disposition, but you track all previous moves that have been made, and then you continue to maximize expected utility. So it's not really a moral strategy at all. Tit for tat, you could attribute moral properties to, but maximizing expected utility is just an amoral strategic plan that actually tends to work extremely well, in particular populations.
Professor, not to interrupt, but I get the
No, go ahead.
feeling the maximized utility is actually based on then repeated equivalent retaliation or the equivalent cooperation, right? I'm
Well,
assuming.
okay, good question. And it doesn't matter what you see. The whole point, if you recall what maximizing expected utility means, it's remember, it's a sum of products. And you're going to say, well, the expected utility of cooperation is what? It's the probability of mutual cooperation times the payoff or the utility plus the probability that you cooperate, the other one defects, times the utility of that. That's the expected utility of cooperation. The expected utility of defection is the probability that if you cooperate, the other one defects, times the utility to that of you, plus the product of the probability that you both defect, times the utility of that. And then once you know the expected utility of cooperating and the expected utility of defecting, you simply choose whichever is the larger number, because you're getting a number out of this. And that's how you maximize it. Maximize it simply. Maximizing expected utilities just means picking the larger of the two. One of them has to be larger. So you just choose the larger one. Now, to your question, in an iterated game, what my strategy was doing was that it was assembling a matrix based on all past history of moves between the two strategies. So if the game was 1,000 moves, it would start to build up an inventory of all previous moves. And based on that inventory, it was assessing the probability as an empirical frequency. So it knew how often each of the four outcomes had been attained because of the history of the game. And then it could simply, on each occasion, compute, of course, very rapidly, instantaneously. It could compute the expected utilities using that matrix of previous outcomes as the basis for the probabilities. And of course, the utilities are fixed because the payoff structure of the prisoner's dilemma was fixed from the beginning, and the payoffs themselves didn't change. But the probabilities evolved over time as the two players developed a history of play. And so that's how it worked. And it was very, very efficient, extremely efficient in terms of its ability to compute expected utilities based on these frequencies. Of course, the larger the number of moves in the game, the more accurate one's assessment of the probabilities would be. If you're only playing 2 or 3 moves, you would not get statistically significant probabilities. But if you're playing 100 moves or 500 moves or 1,000 moves, and actual odds tournaments were all of that order of magnitude, and so were mine. If you're playing 1,000 moves, you can get pretty good statistics, yeah? And so that's every strategy against every other strategy. And then there are many things you can do in terms of how you assess the actual overall winner. So if you're interested in that sort of line of research, then definitely there's quite a considerable literature. And if you want to know more about it, I haven't uploaded anything, but if you're really interested in it, email me and I'll send you some references. All right.
Right.
But
That's,
good question. Yeah, good question.
yeah, I get the principle. It's same as the Josephus problem. Yeah.
Okay, I'm not sure what that means, but in any case,
No worries.
you use probability to compute probabilities. You're looking at empirical frequency. Okay, that's the empiricist view of probability. All right, it's not the Laplacian subjective view, because we don't have enough information to compute that. We need to have experimental data in order to compute empirical probabilities. Yes.
Yes.
Good. Okay. And I mean, this takes us into philosophy of probability, and that's quite an important subject, but a little bit off the beaten track. So anyway, I just wanted to mention those things to you because they are important. And we're going to come back to maximizing expected utility anyway in a few minutes when we look at the 2 alternatives that you are all going to be facing in Newcomb's problem, which is a game, hypothetical game, and a very interesting one. So just let me now introduce Newcomb's problem. Listener, are there any more questions about the prisoner's dilemma? Anything else about last week, either in the one-shot case that we assessed, or 2-player case, or indeed, as we did on Thursday, the n-person dilemma? Any other questions about that? Very well. The Newcomb problem is only a 2-person problem. So it's going to be you and the other player is not a prisoner, but rather a Maxwell's demon who has a lot of money and wants to give it away, as we'll see momentarily. So it is a 2-person problem, basically, but with some interesting constraints. Although it is a prisoner's dilemma in its structure, it has a kind of twist. And that twist has to do with the demon, who's a predictor of what you're going to choose. So in philosophy, we have a whole catalog of paradoxes that arise from this so-called factor of time. Once you throw time into the mix and start playing either with predictors or with time travel, one then will see this emergence of a whole different class of paradoxes, some of which are really quite unresolvable, owing to the nature of our limitations and our knowledge about time itself. So you get this in science fiction too, because there are lots of good science fiction and probably some very bad science fiction dealing with exactly the same theme. And I'd be surprised if some of you hadn't seen movies that you've probably seen movies I haven't seen based on this. But just looking at the paradox of time travel itself, it's not impossible. That is, travel backwards in time does not necessarily, as far as I understand, defy any laws of physics, but it certainly poses interesting paradoxes to us ontologically. For example, if you were to build a time machine and travel backwards in time, what would happen if you then influenced events such that your own parents ended up not meeting each other, and then so as a result of which you weren't born? So this is a theme you see in science fiction all the time. So if you go back in time and interfere with events, and it could be something very small, you could go back to prehistoric times and just kick a stone, and this could have over time, chaotic effects on the evolution of the planet. And some little thing you did could divert the whole course of biological evolution and result in you not having been born. But then if you were never born, how would you ever go back in time to affect that? So that's a bit of a paradox, is it not? Is everybody in shock this morning from this? There are many science fiction stories that attempt to treat this. And I suppose there are other kinds of stories that we could also concoct dealing with people who, let's say, went to the future and learned things that we ourselves didn't know, and then came back to the present day and attempted to use that knowledge perhaps in some way to profit. And so they may also change the future by virtue of what they're doing in the relative past. And that means that what they knew about the future would not necessarily be so either, because they themselves, by bringing that knowledge back to the past and implementing it in some way, might affect the future. And so you have the mirror image of that paradox. So is that the plot of Back to the Future? I'm not sure. Amir, you tell me. I'm a little bit derelict in my movie watching. I tend to read and write more than I watch movies. So, of course, I've heard of that movie, but I'm not sure what it's about. You tell me. Is it something about a time travel paradox?
Well, yeah, basically the main character goes back and accidentally prevents his mother from the critical moment where his mother falls in love with his dad,
Ah,
and she falls in love with him. So there's a whole point where basically, I guess, since it's not he's it's ambiguous because it's not like the parents can't yet, like there's still a chance they can meet, but clearly the critical moment where, like his parents described, they instantly fell in love, right? That love at first sight didn't happen as it's supposed to be.
so
So
then how could they have described it to him? You see, this
right.
is exactly the problem. This is exactly the paradox. So they're describing he's in the future now, and his parents have already met and married, and they've conceived him. But if they told him this and he goes back to the past and changes it, then it couldn't have happened. Then how could he be there? And if you're telling me that she's falling in love with him and not his father, then there's a whole Freudian element to this, then, which is dealing with the Oedipus complex. And I certainly, so he's also bringing Greek mythology into it, and Freudian psychology, it sounds like. So it's maybe it is worth watching. Is this a one-off movie or is it a series?
Well, the first one is one off, but technically there's two other. I would say I would recommend the first one and the second one. The third
I
one, not
will.
so much.
I will have a look over the break. Has Michael J. Fox got anything to do with this?
Yes, actually, he's the main character.
All right, I picked that up out of the out of the ether that lodged in my brain somewhere. So I'm making that connection. Okay, well, thank you for the tip. I'm going to have a look. So it seems to be addressing exactly this kind of problem, and I have no doubt that there are many other science fiction stories in print, whether they've been made into movies or not. Which deal exactly with this. So you see that it's a paradox. As soon as we start introducing time travel, we can sort of unravel our commonsensical notions of how causality works. And we're going to encounter this in the rather Newcomb's problem in just a few minutes. The other thing I wanted to mention to you is that there are a number of other paradoxes that are still being debated by philosophers that are not really resolved, although some people claim to have resolved them. One is the Sleeping Beauty problem. Have any of you heard of the Sleeping Beauty problem? I'm not talking about the movie now by Disney or the fairy tale about the famous fairy tale of Sleeping Beauty, but I mean the Sleeping Beauty paradox. You haven't heard about that? Okay, well, I'll get ready to scratch your heads over this one. It's very simple, like most of these things. It's easy to relate, but much more difficult is a conundrum. Again, owing to this business of twisting time or playing with time. So here's the Sleeping Beauty. There are many versions of it as well, but here's a simple version, or one version of the Sleeping Beauty problem. It turns out that people are voluntarily participating in an experiment, we'll say, where they're going to be put to sleep and then awakened sometime later. But they're either going to be awakened once or twice. And this depends on the toss of a coin. So imagine that you're put to sleep on a Sunday, and then in advance, you're told this, that they're going to flip a coin. The experimenter's going to flip a coin while you're sleeping. And if the coin comes up heads, it's a fair coin. If the coin comes up heads, they're going to wake you up on Monday, and that's it. Okay, yes, that's right. I'm a binary result. If the coin comes up heads, let's say they wake you on Monday, and if the coin comes up tails, then they wake you on Monday, but then they put you back to sleep with a drug that makes you forget that they woke you up on Monday, and then they'll wake you up again on Tuesday, and you'll have no memory of having been awakened on Monday, nor will you know what day it is. So you understand, if the coin is heads, they wake you on Monday and that's it. If the coin is tails, they wake you on Monday, but then they put you back to sleep and you won't remember having been awakened, but then they wake you up again on Tuesday. But you just don't know what day it is. They haven't told you that yet. So the problem then is, when you wake up, what day is it? Okay. What are when you wake up from this, what evidence do you have to believe that it's a Monday or a Tuesday? What is the most likely day? Is it a Monday or is it a Tuesday? You know everything I've just told you, but you don't know whether the coin came up heads or tails in your case. So there's a debate about whether you have a better reason to believe it's Tuesday or a better reason to believe it's Monday, or in fact, whether you have no reason to prefer one choice as being more credible than the other. And that, in a nutshell, is called the Sleeping Beauty problem. So again, it's playing with time and playing with memory in an interesting way. All right, Amr, you seem to have heard of this, also, given your synopsis. All right, so these are the kinds of problems that enter when we start playing with time and predictors as well. So we're now going to segue from that into the actual Newcomb problem. And the Newcomb's problem is still being debated. It's a very interesting problem indeed. And it's simple, again, as a game, but fairly complex in the way in which one could justify one of the two choices. So you can look, Amr, if you're interested in that, you can also look. There's a vast literature. All you have to do is Google the Sleeping Beauty problem, as opposed to the Sleeping Beauty fairy tale. But the Sleeping Beauty problem, lots of philosophers have been debating this for quite some time. And I don't think there's really any consensus. So, and there are mathematicians also that have chimed in, and people working on actual probabilities, seeing what the most correct way to frame it is. But anyway, let's go now to Newcomb's problem. The first reporting of this was 1969. Newcomb's problem was first published, although it had probably circulated verbally. Obviously, there was no internet in those days. So 1969, by a Harvard philosopher who's now deceased, very good philosopher, named Robert Nozick. And he published an account of Newcomb's problem. I'm entering this also. The problem itself was called Newcomb's problem, supposedly discovered by a physicist named Newcomb, hence it's named after him. But it was first reported by Robert Nozick in 1969 in a collection of essays devoted to Carl Hempel, the philosopher of science. Very, very interesting essay that he contributed, and this problem has then been discussed ever since by philosophers, and there's a huge literature on it. So I'm going to describe the problem to you today, and I'm going to each of you is going to be able to actually decide what you would prefer to choose, and then we'll have some discussion about your choices. And then on Thursday, I will actually look at some very unexpected applications. Newcomb's problem, although it looks just like a hypothetical mind or thought experiment, it turns out to have some interesting applications as well. And we'll look at those next day. But to the problem itself, I will now endeavor to share the screen with you. So bear with me, please, while I do that. Let's see if we can share the screen today. That looks like it's here. Okay, is everybody now see Newcomb's problem on your screen? Yes? When they open the chat room? You do. Okay, thank you very much. So I have the chat room open, and I'm going to just pose the problem to you, and then we'll see that it turns out to be straightforwardly a special case of a prisoner's dilemma. Therefore, what's interesting to us is that the principles of choice, it's a one-shot game. You get to play this once with the demon, and it turns out that your principles of choice will therefore be conflicted, just as they are in the prisoner's dilemma. But the setup of the game is a little bit different. So this is what it is. There's a character in this game called Newcomb's demon. All right. And the demon is not a bad guy. The demon is actually very wealthy and is very happy to give away money. The demon really has only one interest in this game. The demon is so wealthy. Demon's wealthier than Jeff Bezos. The demon doesn't care how much money it gives away. It's got money to spare, and it's happy to give the players money. You each get to play once. Imagine that you all line up, take a number, and then you get to play one at a time, and you get to watch. It's really important that you actually get to watch what's going on and see how the other players do until your turn comes, and then you play. So what the demon wants actually is to make correct predictions. So I say the demon it doesn't care about money. It has lots of money, but the demon really has an interest in predicting what each player is going to choose to do. And that the demon turns out to have a great talent. And you can watch this game being played many times before your turn comes. And you could see that the demon uncannily predicts with a huge success rate what each player does in turn. And it's almost a near perfect prediction rate. So here's the way the game works. First, the demon is going to predict what you will do. And you will do one of two things. What you're looking at when you step up to play are two boxes, box A and box B. And box A is transparent, so you can see what's in it. And in fact, it contains $1,000. And you could see it, and that money is yours if you want it. Box B, however, is opaque. So it's gift wrapped. You can't see into the box. You see the gift wrap. I've covered the box B with sort of gift wrap, so you can't see in. But you know for sure that it's going to contain either $1 million or nothing. And this depends on what the demon predicts about you. So, okay, the first thing that happens is that you step up and you see box A, transparent box, $1,000 sitting there. Box B, you can't see inside. Now the demon will look at you and then predict what you're going to do. And your choice is as follows. You can either take both boxes. If you say you want both boxes, then you're going to get the $1,000. But if the demon predicts that you will choose both boxes, it puts nothing in box B. So that your first choice is to take both boxes if you want them. So you get the contents of both. Your other choice is to take box B only. And if the demon predicts that you're going to choose box B only, it puts $1 million in that box. But if the demon predicts that you're going to choose both boxes, it places nothing in box B. Are we clear so far? So that's the strict sequence. So first you step up, you look at both boxes. The demon then predicts what you're going to do. And if it predicts that you're going to choose only box B, it puts $1 million in box B. If it predicts that you're going to choose both boxes, it puts nothing in box B. And then once the demon will have made its prediction about you and either placed $1 million in box B or not, depending on what it predicts, then you choose. And you choose either box B only or you choose both boxes. And then you'll see what you get. If you choose both boxes, you'll obviously get the contents of both. If you choose box B only, you'll get whatever is in box B. At that point, you'll know. Is this clear about the sequence? Do you understand, firstly, how the game is played? Before we move on to the decision principles at stake, I mean, why would you choose both? Why would you choose B only? Do you understand the sequence of play? It's very important that you understand. This is the way the game unfolds in these strict sequence of moves. So is that okay for everybody? Yes, you understand how the game is played. Okay. You're saying yes, so that's fine. And then the next player steps up, then it's all reset. The next player steps up and the same thing happens. And you get to watch. What's really interesting is that you get to watch each player. And so you could see that the demon is uncannily successful at predicting whatever the players choose. The demon is able to predict quite uncannily well. All right. So now I'm going to go back to the, I'm able to do this. All right. Can you now see the next slide where I've set up the matrix of the game? I just want to make sure you still see. Okay, fine. Thank you.
We can see.
Do the players know what the demon predicts? Alejandra, I'm going back. Of course, the players don't know what the demon predicts until they make their choice. All right. Once you make your choice, you'll know what the demon predicts. That is, depending on the choice you make. If you choose both boxes, Alejandra, then the demon, if the demon correctly predicts that, you will get nothing from box B. Yes? You get the 1,000 in A, but you'll get nothing in B. If you choose box B alone and you find $1 million in it, you'll know the demon will have correctly predicted that you would choose box B alone, right? But you're not going to know what the demon will have predicted until you actually make your choice, because that's the sequence. Number one, the demon predicts what you'll do, and then it responds accordingly. And then only when you will have chosen will you know ultimately what the demon has already predicted. Is that clear? That's the order of the moves. It's very important. Okay, is that clear? Okay. You're welcome. So now let's look at the actual problem. So no, the demon doesn't, of course, Amr, the demon doesn't tell you what it's predicting. The demon is merely predicting what you're going to do. The demon's like, imagine this. Maybe I wasn't clear enough. The demon's reading your mind. Let's take that as a plausible way that the demon is predicting. The demon's going to look at you and read your mind. All right, let's pretend that. That's consistent with the problem. So the demon reads your, if it's your turn, the demon reads your mind. And so based on its reading of your mind, it predicts whether you're going to choose box B only or both boxes. So it's reading your mind. And then if it predicts, if it sees in your mind you're going to choose box B only, then it puts $1 million in that box. If it sees in your mind that you're going to pick both boxes, it puts nothing in that box. Okay, so only after you make your choice are you going to figure out whether the demon predicted correctly or not. But what you are able to observe, remember, this is key. You're watching all these people in front of you, like everybody in the class is lined up to play this game. And what you notice consistently is that the demon is almost 100% correct, almost perfectly predicting what each player is going to do, because you definitely get to see the player's choice. They're going to make that verbally. Each player is going to say either I'll take box B alone or I'll take both boxes. And you're able to see if they take box B alone, whether it's got $1 million or nothing. And you're able to see that uncannily, almost every player who says I'll pick box B alone finds it has $1 million in it. And almost every player who says I'll take both boxes finds nothing in box B. And gets the 1,000, of course, but gets nothing from box B. So what you're able to conclude as observers of this experiment is that the demon has an uncannily high success rate. Maybe 99.99% of the time, the demon is correct in its predictions. Clear? Everybody good? Alrighty. Very well. So here's the way the game looks if we now set it up in a matrix representation. We will very quickly see, by simply looking at the choices and the payoffs, that in fact it's a special case of a prisoner's dilemma, which is what makes it really interesting. I mean, partly what makes it really interesting, because if you look at you as, you know, in this case, you're the player, and you look at the demon, right, who's predicting your choice in each case. So your choice is either going to be box B only or both boxes. That's what we've said. But before you make that choice, that's why you're in this case temporarily position 2. Before you make your choice, the demon will make its prediction about your choice. So if the demon predicts that you'll choose box B only, it puts $1 million in there. If the demon predicts that you'll choose both boxes, it puts nothing in there. All right. And then naturally, if you choose if you choose box B only, you're either therefore going to get $1 million or nothing. Yeah? Those are the only two possibilities. If you choose both boxes, you're either going to get $1 million plus 1,000, because box A has 1,000 in it. That's not going away. If you choose both boxes, you're going to get that 1,000. If the demon predicted that you would choose box B only, and predicted wrongly in that case, where you chose both, then you're going to get $1 million plus 1,000. But again, if the demon predicted correctly that you would choose both boxes and you choose both boxes, then you only get the 1,000 that's in box A, right? Because if it predicts you'll choose both, it places nothing in B. So that's a matrix representation of the 4 possible outcomes for each round of this game, as each one of you plays against the demon. But you'll notice something immediately particularly if you've been attentive last week, that the payoff structure is precisely the same as a prisoner's dilemma, where the temptation to defect is, or in this case, is represented as the temptation to take both boxes. And that's greater than the reward for believing in the demon's correct prediction and so choosing box B only and getting the million. And that in turn is greater than the punishment, as it were, for disbelieving in the demon's ability to predict and choosing both boxes. And that in turn is greater than the sucker's payoff, where actually the sucker's payoff is nothing because you actually believe in the demon's predictiveness, and you believe that if you choose box B only, the demon will have predicted it and put a million in there. But in your case, unfortunately, and it almost never happens, but in that case, the demon was wrong and predicted both, and you chose B only, and so you got nothing, and that's the sucker's payoff. But you see that it's exactly the same payoff structure as a prisoner's dilemma, with the one caveat that we have set S to 0 in that case. And of course, T equals, as it happens, T in this case equals R plus P, right? This thing is equal to this plus this. So those are some constraints that are placed on the actual utilities, but they do not do any violence to the structure of this thing, which is exactly the structure of a prisoner's dilemma. So is that clear? Are we good so far? Do you understand by just inspection of the matrix that it's a prisoner's dilemma? Yes. Okay, Lenise, excellent. Is everybody okay with that? And if you're not okay with it, go back to last week's slides. These slides are up in they're all in your Google Drive folder, so you'll be able to look very quickly at the earlier prisoner's dilemma slide and see it's the same ordering, right? Remember, what makes a prisoner's dilemma in terms of the payoffs, not in terms of the ground rules, but in terms of the payoffs, is just this specific transitive ordering of the payoffs. Every time that ordering is respected, we know we have a prisoner's dilemma on our hands. Okay, fair enough. So now that we know it's a prisoner's dilemma, we can apply exactly the same reasoning that we applied in the actual prisoner's dilemma to Newcomb's problem. And we can say to ourselves, but now we already know from our prior experience with this model that we're going to have two conflicting principles of choice, dominance versus maximizing expected utilities. We know this from last week, that it's a dilemma precisely because we're going to have two conflicting principles of choice. Now, some of you, and I don't doubt some of you may already have decided that when your turn comes in this game, you may already have made up your minds whether you'll choose box B only or both boxes. That's fine. But before I ask you, I want to at least complete the task of justifying the decisions, both of them, with these divergent principles. And that's what the next slide will do. So, as you may recall from last week, the dominance principle is very clear. It's going to argue as follows. Look, if you're the player looking across the rows, as you are here, you're the player. Well, it seems that if you choose both boxes, the outcome of choosing both boxes in this case is better, because if the demon predicts box B only, and you choose both boxes, you're going to get a million plus 1,000, even though the probability of that is very small because the demon's predictive success rate is very high. Nonetheless, choosing both boxes gives you a better payoff in this case than choosing one. And here, obviously, choosing both boxes gives you 1,000 guaranteed, whereas if you choose both and the demon correctly predicted it, he'll put nothing in box B. But basically, you're still going to be better off choosing both boxes, no matter what the demon predicts. Dominance says a million plus 1,000 is better than a million, and 1,000 is better than nothing. So obviously, dominance dictates that you choose both boxes. Are you clear about that? Once again, the same as in the prisoner's dilemma. You may recall the argument is that you're better off defecting no matter what the other player does, because T is greater than R and P is greater than S, based simply on the transitive ordering of the payoffs in the model. Is that clear? Everybody okay? Anybody okay?
Yeah, I think so.
Good. Okay. Thank you. Thank you, Mariana. Thank you, whoever is speaking. You see that dominance says you're simply better off picking both boxes, no matter what the demon predicts. Yeah. So that would be a reason. That would be a reason to choose both boxes. You're simply better off based on the payoffs. But now we have the conflicting principle, and this is where, once again, you need to maximize your expected utilities. And if you maximize your expected utilities, you may already realize you're going to get a very different result. Why? We're going to suppose that the demons, again, as we've argued all along, one of the suppositions in the model is that the demons' rate of correct predictions is very nearly perfect. So that means the probability that the demon will correctly predict what you're going to do is very nearly 1. And the probability that it will incorrectly is very nearly 0. So let's assume, as we did in the prisoner's dilemma, complete probabilistic dependence. We'll suppose, therefore, that the demon is a near perfect, or for the cases, or for the sake of argument, a perfect predictor, very near perfect predictor, which means that, yes, it means that if you will choose both boxes, the demon will have predicted that with very nearly perfect success rate. Yes? And so that means that the expected utility of both boxes is going to be the expected utility of this choice, which is going to be basically probability of almost 1 times 1,000. So the expected utility of both boxes is only $1,000. Whereas if you choose box B only, once again, the demon will have almost certainly predicted this. And so the expected utility of choosing box B only is a probability of almost 1 times a million, which is approximately a million, and a probability of very near 0 times 0. So that your expected utility of box B only is going to be almost $1 million. Whereas your expected utility of both boxes is going to be only $1,000. And since I don't have to convince you that $1 million is much greater than 1,000, 1,000 times greater than 1,000, the expected utility of box B is therefore very much greater than the expected utility of both boxes. And therefore, maximizing your expected utilities indicates that you should choose box B only, because you're going to get almost certainly $1 million if you do that, because the demon will have predicted it almost perfectly. Whereas if you choose both, the demon will have predicted that too, and there will be nothing in box B, and you're going to get the 1,000 for sure, but not the million. So you should obviously choose box B only, given the demon's high success rate. But interestingly, as with the prisoner's dilemma, it should not surprise you that, in fact, maximizing expected utilities will prescribe that you choose box B only, even if the demon's rate of successful predictions is not even that close to perfect. As long as it's more than a half, it turns out that the relative frequency of correct predictions, you keep observing all the players who go in front of you, and you can keep track of whether the demon's predicting their choice correctly or not. And you can kind of do the probability based on that frequency that you record. And if the demon does better than a half, then you're still going to be better off, according to maximizing expected utilities, that is, with a successful probability of more than a half, box B will be prescribed, not both. Whereas, again, dominance says, well, obviously, you're better off taking both no matter what. So those are your choices. And I hope you understand that the two principles that diverge are exactly the same two principles that we already saw diverging in the prisoner's dilemma. And it shouldn't surprise us, because this is a very exotic, very special case of the prisoner's dilemma. So again, you can either choose both boxes, or you can choose box B only. Now, let me ask you a question, since we're now in class, back to class. I'm going to stop the share momentarily. We're coming back to reality, and I'm going to ask you to pretend for a moment that you're actually playing this game. I want you to pretend that you've now taken a number, you've queued up You're online to play this game. The demon's sitting there. The demon has bags and bags of money to give away. The demon doesn't care about whether everybody picks box B only and it predicts that correctly. So it gives $1 million to each of you, or indeed whether you choose both. And you're either going to get $1 million plus 1,000 or just 1,000. And the demon will keep replenishing the money in one or both boxes, depending on, again, its prediction about you. But each player, the demon's never going to run out of money. And the demon doesn't care about giving away money. Remember, the demon only wants to make correct predictions about what each player is going to do. And as you're watching those in front of you play one by one, you're able to witness that the demon is uncannily successful. The demon seems to be reading everybody's mind. And so it's able to predict most of the time, almost perfectly, what each player will do. So then it comes your turn. Now imagine it's you. You step up. And the demon takes a look at you, and the demon's reading its mind. And then there's a curtain lowered so you can't see temporarily. The 1,000 is in box A because it's there, but then you can't see whether the demon's putting $1 million in box B or not, because that depends on what it predicts about you. And then the curtain's drawn. The demon's looking at you, smiling and saying, okay, do you choose box B only, or do you choose both boxes? All right? So now what I want you to do, if you don't mind, is just type into the chat room, box B only or both boxes. Okay, just go for it. Box B, box B, box B. Okay, somebody said both before. There's a great, okay, box B. Most of you so far are going for box B only. Okay, one of you earlier said you were going to take both boxes. And of course, that's a legitimate choice. You're guaranteed 1,000. I see a lot of you are seem to be believing in the demon at this point, and so you're hoping for that $1 million, aren't you? And indeed, you have a high probability of getting it, according to maximizing expected utility. So far, we have almost unanimous those who've entered. Can the demon be predict? I don't understand the question, Taisha. Could you explain the question? The demon's not flipping a coin. The demon is. It could never be that accurate. If it flipped a coin, it would only be half right, half the time, right? So the demon is somehow reading your mind. That's what you need to imagine. So most of you are choosing box B only, and your choices are 50-50. What does that mean? Your choice is not 50-50. Your choice is your choice. I mean, your choice is 100% what you choose it to be. Do you mean, Taisha, that you'd flip a coin? Is that what you're saying, that you would rather flip a coin? That's interesting. That would be really interesting. So if you yourself were indecisive, and I want to discuss that for a moment, because that's not really technically one of your choices. But since we're assuming in the background that you have some principle, some decision principle behind your choice, if you made it completely random, that's really interesting proposition. Okay, do you remember back to the prisoner's dilemma? And what we said about maximizing expected utilities? We said that, and we showed this with algebra, that in fact, if you believe that your fellow prisoner has a greater than 50-50 chance of cooperating, then you should cooperate. Do you remember that discussion last week? If you're trying to maximize expected utilities in this model, cooperation is prescribed. Cooperation in the Newcomb's problem is equivalent to choosing box B only. But in the prisoner's dilemma, cooperation is prescribed just in case you believe that the probability that the other player cooperates, if you do, is more than 50-50. If you happen to know or happen to believe that the other player is going to flip a coin, then that player's probability of cooperation is only 50-50, and therefore less. It's not greater than a half. It's only a half. And in that case, maximizing expected utilities will dictate that you defect. That's a very important argument, that you should only cooperate if indeed you believe that the probability of joint cooperation is 50-50, is greater than 50-50. But if your opponent's going to flip a coin, then you have to defect in order to protect yourself. And so I'm saying to you that the demon, if you remember that argument from the prisoner's dilemma, that if the demon reads your mind and knows you're flipping a coin, then I would say the demon, based on that logic, the demon's going to put nothing in box B. That's, if I were the demon, that's what I would do. Let's put it this way. If I saw you legitimately making a decision in your mind, I could read your mind, right? And then I'd be governed by the rules of the game. But if I saw you choosing to flip a coin, then I would say, well, you're making it impossible for me to read your mind. And so I'm basically going to put nothing in box B. I'm not going to reward you for failing to make a choice. So I think the demon, I don't know, and nobody knows, but I would be inclined to think the demon would punish randomness by putting nothing in box B. All right, that's my without any. There's no other information in the given to us in the problem, and it's not technically allowed that you flip a coin. It's technically supposed that you're a rational being, by the way, and that being rational technically implies that you're going to have some principle in which on the basis of which to make a choice, and you wanting to flip a coin indicates that maybe you're willing to leave a very important choice up to chance. And I guess some people might prefer to do that. That's like a third option, Taisha. But you are complicating the model by introducing this third option where the player makes a random choice. That's not strictly in the rules. Okay. So I like the suggestion. It leads to many more complications. But technically, you're not allowed to flip a coin. You have to just say, okay, I choose box A, or I choose B alone, rather, or I choose both. Is it fair enough? I wanted to respond because I think your question merited it, but technically it's not in the ground rules. All right. So it's not allowed to be random. You have to really make a decision, and therefore, in some sense, commit yourself to dominance or to maximizing expected utilities. And so Heidi picks both. And that's, I think, this morning, a majority of you have picked so far, those of you who have disclosed, certainly not everybody, right? These aren't mail-in ballots, folks. I'm asking you, I'm not mailing out ballots to you. I'm asking you right now to type in whether you choose B only or both boxes. So we get a real-time estimate. There are 59 of you in the room, and I see roughly maybe 15 or 20 votes on the table at the moment, or not votes, but rather your choices. And so I see the majority of you are choosing to take box B only and hoping for that $1 million, obviously. And according to the logic of the problem, you have a very good chance of getting that $1 million. But I want to tell you what usually happens. The first time I've ever done this virtually, and normally you do this in the class, and there's no difference in how I present it. But I'll tell you what Nozick found. And Nozick used to teach this at Harvard, and he did it every year with his, he had various classes, and he would bring this problem up because students always find it interesting. And Nozick revealed in his actual essay, when he first discussed the problem and presented it to other philosophers, he said he always found, almost always found, that his classes divided about 50-50, with around half of them choosing box B only and around half of them choosing both boxes. And moreover, he said that when they discussed it, each half of the class thought the other's choice was kind of silly or unwarranted. And I've been doing the same thing at City College for many years. I always present this paradox or dilemma. And usually, and this today is an exception, but usually the class also divides around 50-50, and sometimes even more to both boxes. And again, the people who choose both think the people who are choosing box B only are being silly or foolish, and vice versa. People who choose box B only often think people who choose both boxes are silly or foolish. So there's no right answer to this. Because we're not playing with real money, nor could we. But you have to then justify your decision in some way or another. And so it almost always divides up. Would anybody like to say why? Since quite a number of you chose box B this morning, would anyone like to say why they chose box B?
Well, Here's the thing, Professor, but I'm gonna say my reason, but I also want to make a prediction as to why, for instance, what you and Resnick, when you Resnick,
Nozick, yeah, go ahead.
Nozick, sorry, each always basically it's sort of an almost even split. Um, so my reason for choosing box B is, as you would say, the even above like in a situation where you know that the demon always has an above 50% of correctly predicting your choice,
Yep,
you would always want to go for the max maximum maximize expected utility in that
correct.
choice, right? And that's basically me backing my choice with the statistics of it, right?
Yes,
Like,
exactly. The statistics will bear you out in the way
right.
the experiment is. Yes, the statistics will always bear you out. But I want to give you the other argument. I love being the devil's advocate. I'm not the
Well, that's
demon's
what.
advocate.
Wait, Professor, and I want to hear what you actually risk. I just want to make a prediction. I
Go ahead.
think that the people who choose both boxes are basically like, yes, the statistics might show that, but to me, the fear of being the sucker is so much greater that I'd rather have something than nothing at all. Right?
Sure, sure. And I don't think it's fear. I think it's, I mean, it might be psychologically the fear of being the sucker. Certainly in the prisoner's dilemma, Amir, in the generic prisoner's dilemma, there is that fear of being the sucker, right? You need to protect yourself against the other prisoner, right? Obviously. But in this model, you have nothing to lose. If you choose both boxes, you're guaranteed a minimum of 1,000. Whereas if you choose box B only, you're not guaranteed that minimum. You're either going to get a huge payoff of 1,000,000 or nothing at all. Yeah. So here's the argument. Now your point is well taken, but I think that people, and we have one person who chose both. So Heidi, why did you choose both? Would you like to share with us, or can you?
I chose both because I thought, like what you said, at least I would have 1,000, and it's better
Right.
than nothing.
Exactly. I mean, and that's exactly the dominance reasoning, is that the demon has already done what it's done. Just to develop your thought a little further, Heidi. I mean, people who choose both boxes, and normally there are more of them, but people who choose both boxes reason as follows: it's the dominance principle. Look, there's $1,000 sitting there, and obviously that if I take both boxes, I'm guaranteed that, which is what Heidi says. I mean, you're guaranteed 1,000. You can't lose. But if the demon predicted wrong about me, and the demon puts 1,000,000 in there, I'm going to get that too. So either way, I'm better off because I'm guaranteed 1,000 in this case. I'm not guaranteed 1,000 if I choose box B only. And just in case the demon was wrong, then I'm going to get 1,000 plus 1,000,000. So dominance will tell you you're better off choosing both boxes. I mean, the demon has already made its move. If you want to look at it even more rationally and understand what dominance is perhaps really saying, dominance is saying, look, it's your turn. And the money is either in box B or not. At this point, box B either contains 1,000,000 or not, right? The demon's already made its move. It can't take anything back. So you're looking at both boxes. You can't see what's in box B, but there's either 1,000,000 there or not. And if you choose box B only and there's no 1,000,000 in there, then the demon's not going to put it there. If you choose both boxes, you're going to get for sure 1,000, and you're going to get whatever in box B. Money can either be put in or taken out at that stage because now it's your turn. So obviously, on that line of reasoning, the demon can't undo anything or redo anything. So the money's either sitting in box B or it's not. You're guaranteed 1,000. Take both and go for the 1,000,000 plus 1,000. And you see, I mean, I'm just extrapolating what Heidi is really, I think, saying and implying, that you're guaranteed the 1,000, but you might also get the 1,000,000. So I think that what you really want is, I mean, here's a more general point, that what you might really want in this game, to be more subtle about it, is actually to be saying to yourself, if you know, like when you step up and the demon's reading your mind, you want to be repeating over and over to yourself, oh, box B only, box B. Like you want the demon to read in your mind that you're going to choose box B only, right? You want to deceive the demon. So I'm being now a bit of more of a conspiracy theorist. I'm saying what I want to do when it's my turn is to think as hard as I can. Oh, box B, box B, box B, make the demon believe that I'm only going to choose box B. So the demon puts 1,000,000 in there. And then when I come up to actually choose, I choose both. So I kind of outwit the demon. And that would be the best of both worlds, wouldn't it? Do you agree, Heidi, if we could outwit the demon, fool the demon into reading that we're going
Yes.
to choose box B only? Then he puts a million in there, and then we come up and choose both boxes, and we get both, the 1,000 plus a million. So, of course, we can't do that because the demon is superior. The demon would know, arguably, that if we were trying to fool it. So it's really reading not only what is in our minds, but it's predicting, moreover, what we're going to do. Remember, those are the conditions of the problem. So in any case, so that's right, Lenise, and that's the justification. You've just said the price for defecting is always better. Yes, the dominant says that you're better off defecting no matter what the other one does, because you're either going to get a million plus 1,000, which is certainly better than a million, or you're going to get 1,000 versus nothing, which is certainly better than nothing. And so you're much better off choosing both boxes. That's the argument for both boxes. Now, I want to share, we have a few minutes. I want to share one more thing with you. In the terminology of the game, now that you've learned to play the game and you played the game, most of you or some of you, you're either a one boxer or a two boxer. Okay, so those of you who will go with box B only, you're called one boxers, and there's a bunch of one boxers out there. And I guess you could join the club, and for all I know, they have a website or some Facebook page for one boxers. Okay, I don't know, wouldn't surprise me. You could join that club. Those of you who choose two boxes, both A, you're obviously two boxers. So you're either a one boxer or a two boxer, and there's probably some club of two boxers too, maybe a Facebook page of two boxers for all I know. So you could try this at home. It's perfectly safe. But I want to say one thing to you more. And there are certain conditions that might influence your choice. So please take this into consideration. If you've got where we are so far, if you've understood what we've done today, you're fine. But I want to throw one more slight nuance at you. And that is the following thing. And this is right across the board when we're looking at utilities. We're looking in this game at money and not at utils. A util, such as a number in the prisoner's dilemma or an abstract value in the prisoner's dilemma, T, R, P, S. These are just algebraic representations of quantities. They're not fixed quantities. They're utile, so they're pure units of utility. But as soon as we start plugging money into the payoffs, we're going to get a certain margin of relative value, because money is not absolutely worth the same to everybody. So, for example, let me ask, how many of you could afford to give $1 to somebody panhandling on the street? Somebody looked really hungry and like they really needed a cup of coffee or something to eat. So, I'm not asking you to betray your conscience. I'm just saying, how many of you would be willing to give somebody, say, $1? Yes, you would, sure. And most of us would, and I do too. And we do. Okay. So that's fine. Because what the game theorist is going to point out is because for you, $1 is relatively affordable. But now if I asked how many of you would give $10, how many of you who are willing to give $1 would also be willing to give $10? No, that's full. There you go. So some of you not. You see, times are tough. Exactly. So in other words, the value of $1 to that panhandler is huge, and for you, it's negligible, relatively speaking, negligible. So you could afford it. But if I said, how many of you are going to give 10? Not as many. If I said, how many of you would give 100? Which would like totally make their day, right? And I'll bet none of you would give 100. Exactly. Okay, agree. So you understand that the value of money is relative. It's not absolute. Because the value of that dollar to the person begging for it or asking for it is really huge compared to your wealth. Whereas the value of $10 begins to be more significant to you. What about Bill Gates? If Bill Gates or Jeff Bezos are walking down the street, they could give 10, they could give 100, they could give 1,000, right? Jeff Bezos giving $1,000 to a panhandler, although he'd never do it, I'm sure, is probably nothing to him. Exactly, Amber. Even 100 is not only nothing to him. 1,000, he's the richest guy on the planet now. He's worth like $70 billion. So he could give $1,000 to a panhandler, would mean less to him than you guys giving $1 or me giving $1. So the value of money is relative to the person who possesses it. So here's my point. Suppose we changed the value in the payoff matrix by a factor of 10, up or down. You see? And I'll just go back to sharing the screen with you, and I'll just leave you with this thought that we could also therefore change the way that we actually are able to elicit decisions based on the payoffs themselves. I'll show you what I mean explicitly. Are you still seeing the screen by any chance?
Yes.
You are? Okay, by some miracle, I didn't stop sharing it. All right. So now suppose we change it as follows. Suppose that there's only $1 in box A. Okay? $1, not 1,000, but $1 in box A. And suppose the demon, because the difference between a million and 1,000 is $1,000 more, right? 1,000 times more. A million is 1,000 thousands. So if we scale this down, so there's only $1 in box A, then according to the ratio of the payoffs, the demon would either put 1,000 in box B or nothing. Clear? Are you clear? What we've done is we've reduced everything by a factor of 1,000. So we've made $1 available to you in box A. It's sitting there, and the demon, based on its prediction of your choices, they're going to put a 1,000 or nothing in box B. I'll bet you if that were the actual values on the table, most of you would take both boxes, because that dollar that's sitting in box A doesn't mean that much to you. You've already conceded that. You could give $1 to someone on the street. It wouldn't mean that much to you. Whereas you definitely want to go for the 1,000. Do you get what I'm saying? So we haven't changed anything. We haven't changed the ratio of the payoffs, but we've changed the absolute value. And similarly, if I scaled it up, and I'll conclude with this, if I scaled it up by a factor of 1,000, let's say now that the demon put $1 million in box A, that's sitting there for you to take, and put 1,000 millions or not in box B, which is $1 billion, depending on its prediction, right? So you've got 1 million sitting there in box A, and you've got either $1 billion or nothing in box B. Now I bet that almost all of you, and I certainly would be strongly tempted to take both boxes and be guaranteed $1 million. You see? Do you see my point? And we haven't changed the ratio of the actual payoffs, but we've changed the absolute value of the payoffs. And that illustrates something simple, namely that the value of money is not linear. Okay, the value of money is not dependent on some straightforward linear valuation. It depends on our circumstances. And I think all of you are understanding that. And so whether you would be one boxers or two boxers, the moral of the story is that whether you're a one boxer or a two boxer doesn't, strictly speaking, depend on the actual problem and the ratio of payoffs in the problem. It also depends on the absolute value of what's sitting, or the absolute amount of money that's sitting in box A, and its relative value to you. So it's a more complicated problem than that. And if we change this problem cross-culturally, and if we change this problem, and asked it of people in economies that were worse than ours, or in economies that were better than ours, or if we went through socioeconomic strata and we posed this problem using different amounts of money, we get very different responses. And we could probably meta predict what the balance of one boxers and two boxers would be by adjusting the raw value of the payoffs to the relative valuation of money according to the subject to the experiment. And that would be something that economists and psychologists would be more interested in than philosophers. I'm going to leave it there. I hope you've enjoyed this. Thank you for your participation today. You can try this at home, see how many of your folks are one boxers or two boxers. And, I do it with the standard numbers. 1,000 and 1 million are pretty good numbers for us to work with. So anyway, see you, my group, I'll see you Thursday, and I will record that lecture. We're going to now look at some very unlikely predictions. Our next and final challenge will be to realize that this model, as hypothetical and bizarre as it may seem to you, nonetheless has some very interesting real world applications. Could I please remind you, when the third essay in your section is due? Yes, it's going to be the week after, Abdullah. It's going to be the week after, the Monday after our last class. So that's going to be the 14th, but I'll announce that on Thursday as well. All right. Have a wonderful week, everybody. Thank you very much.
Thank you, Professor.
Have a great day. Vamos a la
Thank you,
playa, Alejandro. I see that photo again. Okay. Have a wonderful week. Bye-bye
Wait,
now.
Professor. So
Yes.
I just wanted you to repeat what you said when you reduced basically both options. You know, one boxer versus two boxers by a factor of 1,000. You said
Yes.
that what would happen?
Yes,
Because
what would happen is if you reduce it by a factor of 1,000, then you're looking at box A, it's only got $1 in it, right? And the Demons are either going to place now not 1,000,000, but only 1,000 in box B or not, depending on its prediction of your choice. So I'm saying if you're looking at $1 as your guaranteed minimum, that's not so exciting.
right, so then people who might have originally been a two boxer would shift to like from the
Exactly, because they
dominance
want to get
theory.
the 1,000. They don't care about the dollar, but now they
Mm.
want to go for the 1,000. Exactly right. So they would shift from being from being two boxers to one boxers because they would believe they're better off, getting 1,000. They have a higher chance of getting 1,000 if they choose box B only. Whereas if you now shift it upward by a factor of 1,000, now you inflate everything by a factor of 1,000. So you're looking at $1 million in box A now.
And then
Not,
probably
you're looking at $1 million in box A and possibly $1 billion in box B, if
right.
depending again. So I'm saying now the people who are box Bers only, a lot more of them are gonna take both boxes because they're guaranteed $1 million
A
now.
million either way, right?
See what I mean?
Yeah.
So it's also the actual amounts of money, the what I'm saying is that the ratios of the payoffs have not changed at all. We've just deflated them by 1,000 and inflated them by 1,000. So they're still the same ratios. And so the calculus is still the same in both cases. Dominance is still dominance, and maximizing expected utility will still tell you what it's always told you, but the psychology of choice and the economics of choice will be drastically affected by upscaling or downscaling the absolute payoffs.
Right.
You see?
Yeah, no, the basically there's the I guess the right, like what you said, the calculus of the statistical ratios are irrelevant once the absolute values are altered, right? It's saying more like the Newcomb's theory is a lot more based on just like the raw value present in
Yes,
stock.
the original problem is a decision problem, and it's not factoring in socioeconomics. It's not factoring in how much is $1 worth to you, how much is 1,000 worth to you, how much is $1 million worth to you. It's picking an intermediate amount such that people would mostly in the middle class, let's say, where most of us are assumed to come from, we would be certainly tempted by the 1,000, but we would really love to get our hands on the million. Yeah.
Yeah.
So that sets up a tension. All right. If you're dealing with ultra wealthy people, they're not going to care about the 1,000. So you have to inflate it. If you're dealing with homeless people, they're going to care greatly about the 1,000, usually about the 1,000. So you'd have to deflate it. You see,
Right.
in order to run the experiment and expect to get anything like an even division between one boxers and two boxers. So it's the calculus is not dependent upon the absolute value of the payoffs. It's only dependent upon the invariance of the ratios. But
Right.
the actual division of choice is going to depend much more upon the absolute value of the money in the boxes. Okay?
Yes. Yeah.
All right. I think you've got it. Fair enough. Have a wonderful day.
Thank
And
you.
I will see you later.